Hello everyone. Welcome to the Arcteq webinar Wednesday. The topic for today's webinar is capacitor bank protection. My name is Rajkumar and I'm working as an application engineer with the technical support team of Arcteq. Let's go to the presentation. In today's webinar, we will be discussing the following topics: why capacitors are used in the power system, what are the capacitor banks layout, how they are designed and assembled, what is the natural unbalance compensation, how to do with the Arcteq relays, what are the capacitor protection functions available in the IED, and then we will look into this AQC255 Arcteq dedicated capacitor protection IED, and then we will use the Omicron to test some of the protection functions, and then the session ends. First of all, before designing the protection, we must learn that why capacitor banks are used at the first place. Well, the capacitor banks are commonly used to improve the quality of the power system and the electrical power supply for its efficient operation. The main purpose of the installation is to provide the capacitive power to the system and to improve the power factor. We all know that in big industries, there are large amount of inductive loads, like in the inductive machines. They need to consume a lot of capacitive power. So the industry need to use the capacitor banks so that they remain in the limit of their power factor, because they are being penalized if they do not follow the grid codes. This is the general layout of a capacitor bank. The capacitor bank consists of a number of small capacitors, and each capacitor is protected with a small fuse, and then they are arranged in a parallel, as you can see in the picture, and a number of parallel groups are connected in series to form a complete bank. So each fuse is individually protecting a capacitor, a small component of the capacitor bank, and the whole bank is then protected by some kind of protection IED that we are going to learn today. Here you can see each series of components is protected by an internal discharge resistor. That resistor is used to compensate the residual voltage if it goes high. Capacitor banks are commonly used in medium voltage network, and their size stays around 1 MVAR, and they look like this picture. So from the capacitor bank structure, we saw that each capacitor component is protected by a fuse, and then a series of the line of capacitors, those are connected in parallel, is protected by a discharge resistor, and then there is a whole bank. Now what happens here is, when there is an internal fault, one of the capacitor component is isolated from the whole bank when the fuse is blown out. And this does not affect the whole capacitor bank. It stays in the operation and it stays normal. The problem appears when multiple these fuses starts to blow out and multiple capacitors, small capacitor components goes out from the bank. Then, for example, if 3 or 4 capacitors are blown out from the same string, then there will be a voltage stress on that particular string. The purpose is to use an IED to detect those stresses before anything happens or the whole capacitor bank is damaged. So we use capacitor IEDs to detect that unbalance happens due to those fuse, removes the capacitors from the bank. So we find out before it damages the whole bank, basically. The capacitors are designed to withstand 110% of the nominal rated voltage. So normally, under normal condition, they are all working fine, but when they get removed, then they get stress on the whole string. Natural unbalance compensation. We know that the one unbalance that happens due to the fault, that when a fuse blown out, one capacitor goes out from the bank, then the whole stress on that string increases. The number of component, more the component goes out, more the stress increases. But there are also other reasons of unbalance. The primary unbalance is the capacitor manufacturing tolerance. All capacitors are not ideal. They can be different, even of the same rating and same manufacturer. So that also produces an unbalance. Another unbalance created by difference in temperature between different banks and also within the same bank. If the temperature is different in different part of the bank, then it could have a difference in capacitance. And of course, there are those harmonic voltage and currents. Those also affect the unbalance. So basically, these days, most advanced IEDs have this natural compensation that you can compensate whatever there is an unbalance exists there. We will learn how to do that also with the Arcteq relays. So basically, you detect the unbalance or some stress on the IED, on the capacitor bank. You detect it through the IED, and then you set the parameters to produce an alarm, or in worst cases, you can trip the whole IED. The purpose is to protect the whole bank. If the components are, if the capacitors inside the bank are already being removed due to the fuse blown out, so we detect the stress beforehand so that the whole capacitor bank is not damaged. Capacitor protection IED AQC255. This is one of the most unique Arcteq product. It's dedicated capacitor protection IED. This has 4 dedicated capacitor protection functions. Here we have 2 stages of overcurrent, basically overload protection. And then we have capacitor bank neutral unbalance protection. And then capacitor bank current unbalance protection. We will go through the IED software and we'll learn how these settings are done and how the principle, on the basis of principle, it works. So the overload protection. Overload protection basically same as overcurrent protection, but there is something unique about it, that you can do a definite time setting and also IDMT. And IDMT formula here in the IED is most advanced one that customer can use its own user define on the basis of what kind of capacitor banks he is using, and he can draw his own curve. So this is one of the most advanced way that the customer can draw his own curve according to the size of the capacitor and the nature of the capacitor bank as informed by the manufacturer. Then we have capacitor neutral unbalance protection. In the neutral unbalance protection, basically you have 2 stages to produce an alarm if the unbalance goes high, or you can make a trip command. We will also learn how to set these ranges, where to produce the alarm and where to produce the trip. And then we have a capacitor bank current unbalance protection. In this one, we have a number of banks connected in star, and basically it's used between double star type of connection between the capacitor banks, and it monitors the maximum amount of phase current minus minimum amount of phase currents and then divide by the mean. We will also learn how to do this. So this is the capacitor protection IED AQC255. Now I will use the Activate software tool and we will see how these protection settings are performed. So here I'm connected to a relay AQC255. If I go to protection, and I'm also connected with an Omicron, which is injecting voltage and current to the relay. Here you can see the first tab here is C state, where it shows the status of the capacitor. Now it says that the capacitor bank protection mode is activated and capacitor is now connected because I'm injecting some amount of current here. Then we have capacitor characteristics, where you can configure what kind of capacitor bank configuration is done. It's single D, that's delta connection, single Y, that's star connection, double Y, like double star connection, and then H connected. When you select this star connection, you have a capacitor neutral point. You can select as a floating, or you can select this as a grounding. And then here you place the rating of the capacitor banks. For example, how much MVAR it is, what's the voltage. On the basis of that, it calculates the currents. And then you assign what's the tolerance. If we go down in the menu, here you can set the capacitor discharge time, that how much the time it takes to discharge the whole bank. And then here we have capacitor protection functions, overload, unbalance, and neutral unbalance. All these are activated. Once you activate those, they will appear here. This is overload stage 1, overload stage 2. I jumps to directly to overload stage 2. So now it's activated. Its status is normal, and this is what the operating time characteristics look like. And this is user settable. As I said, when I go in settings and I select it as a IDMT curve, so now it follows the curve that's set by the user, and the settings can be found here under the info page. If I go down here, here are some statistics, how many times trips and blocks, what was the last fault, and here are some measurements. And here we have settings, what's the IDMT selection, what's the multiplier, and release time delay. So in the end, here we have the inverse characteristics. This characteristics has 10 points. So basically you can set the curve up to 10 different points. For example, I have selected here 7. And then you can select what kind of curve it is. Is it like 2-point interpolate or 2-point step? So basically when you select the step, it creates a step between 2 points, or you can make a interpolate point. So I have selected here 2-point interpolate, and last 2 are 2-point step. Now if I go to the curve, so this is what the curve is, but of course a customer, a user can make his own curve as the requirement says, according to the capacitor bank they are using. So now if I go to the settings, I see that I have set as a 1.8 time nominal. Now we try to inject more current and see how it performs. Now the status is normal, and I set it to 3 amps each phase. For example, now the protection is started and it starts counting the time, how much time it takes to trip. Well, it take more time, so I increase more current, 5 amps. Yeah, and now it trips. If I go to the registers, I can see that it trips on this amount of current and fault was 3 phase. And if I go to I/O, I can see there is a start signal and then there is a trip signal. So basically, you can make according to your own settings. And if I see the curve, here I can see that it takes, according to this much current, it takes this much time to trip. Yep. I put it off now. So from the settings, here you can select definite time if you want, and if you want to use a user-defined curve, then you can select IDMT. Okay, now we go to this neutral current unbalance. The function is activated, and here we have this natural unbalance compensation. I will show you how to do this natural unbalance compensation. If you see here it says that the measured current is 0, angle is 0, and there is no compensation done here. If I go down, here we have this curve where we assign two points, what should be the tripping point and what should be the alarm point. So if I go, I see in settings that at 300 milliamps, it takes 5 seconds to produce an alarm, and at 500 milliamps time nominal, it takes less time to trip. And first I open the curve, then I show you how it works. Okay, now the inner circle red one is for the alarm and the outer one is for the trip. So I go to Omicron. For example here, and I try to inject, for example, 320 milliamps. Maybe here. Yeah. You can see that it passes the alarm curve, and here you can see that it indicates alarm is on, and then it waits for its, so it started and then alarm is on. And now I try to inject more to bring it to the trip point. So if I inject 520 milliamps, not here, here, now you can see it reaches to the trip point and then the trip is on. If I go in the registers, I can see alarm on and then trip on. And if I go to this I/O, Yeah, we have alarm start activated, then alarm on, and then trip start, and then the trip. So we have 2 points assigned there, and then we see the how much we have this neutral point unbalanced current, and then if it reaches to the point, it produces an alarm or trip. Now we will see how to compensate that. If there is a natural unbalance that we talked before, how to compensate that so that our settings are pretty smooth and the only unbalance appears when there is a real system fault, not on the unbalance that produced not from the fault but some other factors. So I tried to inject here for example 20 milliamps. For example, I assume 20 milliamps are basically a natural unbalance. Here I can read it. If I move this side, here I can see it. What you need to compensate is there is a natural compensation unbalance in use, and then you click on this part and you select compensate. Once you press this, you can see here that the compensation value appears here, and then here you cannot see any natural unbalance there. So basically now what relay does is it converts the unbalance to 0, so there is no any unbalance exists. So basically you can do this when you have a system unbalance, so you just make it more accurate, then your protection will work more sensitive and more accurately. This is about neutral current unbalance, and let's go to the third protection, which is capacitor current unbalance in all the phases. So basically this monitors all the phases, and if there is any difference in the phase current, it calculates the total difference, and then it produces an alarm or trip. So you have alarm, trip, and then it also shows how much the unbalance is there. For example, I go here. Now I'm injecting unbalanced phases. There is phase 1 and phase 3. Phase 2 is 0. So alarm on and trip on. Yeah. Here we have settings. Alarm is set to 1.2 time nominal and trip is set to 1.5 time nominal. So we are injecting more than that, and it's in a trip position. You can also see from here only red and blue phase. There is no yellow phase there, and it trips. Here you have statistics and settings. If I go to IO, yeah, I can see there is a start and trip signal is activated. So we have been through all the capacitor protection functions dedicated available here in the IED, and then there is this RTD when you're using some RTD module, and then if you see in the IED we have all the other protection functions also available, like the current stage, voltage stage, frequency, and some supporting stages. So this is all about IED C255. Thank you so much for listening. If you have any question, feel free to ask. And if you remember something later on, you can send it to our Arcteq support portal. It will reach to us and we will try to answer you. Thank you so much. Have a nice day.